This is the ocean circulation lecture. Just going to share my screen. So what you're going to see from this ocean circulation lecture is it's essentially a continuation of the wind lecture or atmospheric circulation lecture that we left off of. This week, remember, your atmospheric circulation was covered in two parts because it was pretty long. And so this is the third but only second topic that we've covered this week. So third PowerPoint, but second topic. So we did atmospheric circulation first, and that was 2 PowerPoints long, and now ocean circulation. Don't forget, of course, that ocean circulation has a full, large PowerPoint under the content tab with all of the necessary text and all of the necessary notes. This is the voiceover version. And hopefully it helps you, right? Depending on which way you prefer to learn, I offer you both options. So what you're going to notice right away is that we want to remember essentially what we just focused on in the atmospheric circulation lecture, okay? We talked specifically about wind patterns, okay? We started with our easterly direction, right, from the east to the west, going across the equatorial region, which then allows for our trade winds to go clockwise or counterclockwise, north or south of the equator. And you'll notice that these portions of the circulation would match up with essentially the flow and direction of the bottom portion of the atmospheric circulation lecture. We also know, of course, that this is our warm band because it is our tropical region. Okay. Similarly, we have our westerly movement. Okay. Again, both north and south of the equator. So what we've done is we've culminated our wind patterns and now just laid them literally on top of our ocean patterns. What does that mean? Well, it means essentially that the bottom portion and top portion north of the equator of our ocean circulation is primarily responsible by wind. In other words, we call it wind-driven ocean circulation. Now, this is the surface layer of the ocean. So if you remember, this would be our easterly wind or our trade winds. This would be our westerly wind. This would also be our easterly wind, again, southeasterly instead of northeasterly. And this would be our westerly. Okay, so the top and the bottom of these circles are wind-driven circulation. I also refer to those as horizontal, okay, for obvious reasons, because think about how wind blows, okay, horizontally across the surface. So we now know that we have ocean circulation, and we know that at least half of it is wind-driven. The entire periphery, though, must make a complete circle, clockwise or counterclockwise. So that complete circle is actually called a gyre. A gyre is a 4-part circle that goes in the periphery or edge of the oceans. Okay, same down here. Okay, periphery or edge to allow for a complete clockwise or counterclockwise movement of water on the surface layer of the ocean. So what we get is 2 of them being wind-driven, and the other 2, right here and right here, are transverse or lateral, okay? Those are the laterals. That's essentially going to be density dependent, okay? And this entire first section of the lecture is going to cover those concepts. We have 5 major ocean gyres. Remember, a gyre is a 4-part, okay, 4 currents, 4-part periphery of the ocean basin circular movement. This is our gyre, right? Here's the United States. So this is the East Coast, okay? So this is the North Atlantic Ocean. So this is the North Atlantic Gyre. South Atlantic Gyre, North Pacific Gyre, South Pacific Gyre, Indian, okay? These are the major gyres. There are multiple gyres throughout the ocean. What you're noticing, though, is that the top 2 are clockwise and the bottom 2 are the bottom 3 are counterclockwise. You remember this figure from week 8, I believe, No, week 7, when you did the seawater lecture, right? When we talked about it for the seawater lecture, we were looking specifically at just the temperatures because we were talking about density. Well, now what this is telling us is, yeah, we have different densities, warm, cold, and temperate based on temperature. But if you now put the gyres on top of that temperature, it means that you have warmer parts of your gyre and colder parts of your gyre, which makes perfect sense. And that's going to apply to all of the major gyres. Again, this is using thermocline. Remember that fancy term from lab number 5, using thermocline principles. So let's get very specific about just our gyre. Okay, now I already used this term before. We now know what a gyre is. It's 4 currents in the periphery of the ocean basin or the edges of the ocean basin. They are named in the ocean that they're in. And then if there's more than one gyre in an ocean, they name it based on if it's north or south of the equator. So since we are north of the equator, we have the North Atlantic gyre. Okay, we then use our winds. Okay, so here's our easterlies and our westerlies, our winds to move the bottom and the top. Okay, and they move in the direction to which they are pushed. So if the wind is pushing in this direction, then the bottom current must go in the same direction. So it's going from east to west. Similarly with the top. If the westerlies are moving in this direction, from west to east, then of course the top current must go in the same direction. So our bottom current is called the north equatorial current, again, north of the equator, sitting at the equator, north equatorial. The top is called the North Atlantic, because again, it's the northernmost Atlantic current. Those two are wind-driven horizontal surface layer. The other two, one of which you probably heard of before, are called the Gulf Stream and the Canary Current. Those are lateral currents. They run in opposing directions of each other. This one goes from south to north, and this one goes from north to south. And that's because, remember, this entire thing has to go in a clockwise spiral. You know that clockwise spiral and the explanation for that from the Coriolis effect. So we essentially have 1, 2, 3, and 4, right? The whole thing making a clockwise circle. Make sure that you know the names of all these currents and the directions to which they travel. This is what you'll be doing at the end of this portion of this week's lab. Now you'll notice that those 2 lateral currents, the 2 on the side, have different names. They have different directions, but you'll also see that they appear different, okay? So if you remember where the Gulf Stream is coming from, it's coming from a warm current. It's coming from the north equatorial current. So since it's warm, it's less dense, which means it can move fast. So the Gulf Stream, the left side of the periphery of the North Atlantic gyre, cuts very deep and moves very quickly. In opposition, a cold current, that which starts all the way at the top, okay, in the northern portion of the gyre, since it's cold, it's going to move very slowly. It's very dense, so it's very slow. So that one is going to spread out across the surface of the ocean, bringing cold water in a very thin layer, but move in a very slow direction. This is a weak current, and this is a strong current. So what that's telling us is that as we move around our current, and again, this is the one we're focusing on, okay? As we move around our current, they don't move in equal time, okay? So if we have fast, fast, slow, fast, fast, slow, right? So of course we're moving in a circular path, not in a square path the way I drew it, but I wanted to remind you that we have 4 currents, okay? 3, 4 currents that make up the 4 sides of our circle. These 2 are going to be fast because they're warm, and these 2 are going to be slow because they're cold. You'll notice that these currents have blues and reds representing warms and colds, and you'll also see here that there are more than just the 4 main ocean gyres that you saw before. What this does is gives you the entire circulation pattern of the surface layer of the ocean as it applies to circumpolar and essentially all surface layer circulation in the ocean systems. Okay, so that's the very first portion, the very first sort of tidbit of information that you need to understand ocean circulation. Ocean circulation, the wind-driven portion and the lateral sides of movement based on density are literally just on the surface of the ocean. So that surface circulation occurs in the surface layer, okay, meaning the top. It's going to be wind-driven and density dependent. Now that water can't just spin forever on the surface layer like a roulette wheel, right? Laying flat horizontally and never going into the depth of the ocean, because that means that water in the surface of the ocean could never have the opportunity to reach the deep portion of the ocean. But we know that that's not true, because if you put something in the ocean, it can land on the bottom, right? And by something, I don't mean, a sunken ship. That, of course, would apply. But when we're talking about water being added into the ocean, water that has a different salinity, water that has a different temperature, that water can end up on the bottom of the ocean, even if it originated in the tropical regions and vice versa. How does it get there? Okay, so right now, the second part of surface circulation means that we have to explain how to get from the surface of the surface layer through the surface layer to the layer immediately below. Want to remember from lab number 5, the layer immediately below is called the peak neckline, right? So how do we get there? This fancy term that you see here is the description of how the movement occurs, and this fancy term here is the actual physical property. So Ekman transport is a way of moving a net motion of water from the surface of the surface layer to the bottom of the surface layer. It looks like a spiral, hence the name spiral. Okay, so it's the sum of the water direction in the multi-layered ocean, but this occurs only in the surface layer. Each layer in the spiral acts differently, meaning it opposes in a different direction, just like a spiral staircase. Each step is situated in a different angle, in a direction. This is what the Ekman spiral and Ekman transport therefore look like. What it's telling us is that the surface of the surface layer, you have wind-driven circulation. In other words, the wind blows and the water moves in the direction to which it was pushed. Okay? Notice that that surface water is moving in the same direction that the wind is blowing it. Then, as it drops down in the layer of the ocean, from the top of the surface layer to the bottom of the surface layer, as it drops, okay, it's going to be facing and moving an angle 30 to 45 degrees at each step all the way down until you've essentially completed a spiral staircase, right? So this figure here helps you to see that staircase a little better. This stair is a little wider than this stair, and this direction is different than this one, is different than this one, is different than this one, but only by 30 to 45 degrees. They're going to go in a right angle motion all the way around because we pushed our wind and generated our surface water to move in the direction to which it's pushed, but then to fall based on the Coriolis effect. So it will also appear clockwise or counterclockwise, just like the gyre, okay, based on the direction of the Coriolis. Next thing you want to notice is if the wind is pushing the surface in the same direction at the top, the movement of the water all the way at the bottom is going to be 90 degrees to the right from its original source. Okay, so if this is the original, at the bottom, it's 90 degrees on a right angle in the direction from which it originally started. That's really important, okay? See the movement? See the flow? That's really important because it means when the water gets to the bottom of the surface layer via the Ekman spiral through the Ekman transport, the water will then be pushed away from the edge and be able to move and generate into the center of the ocean systems. Remember, a gyre is the periphery of the ocean basin. This is a way of getting water into the center of the circle, into the center of the gyre, so that it can essentially fall down that spiral staircase, gaining speed because it's gaining mobility, right? Because what's actually falling is the water that's the most dense, the salty and the cold water. So when it gets to the bottom, it has a little bit of speed and then can get pushed into the center so that all like water types, all higher density water types can join together in that layer. Okay, one more time, just reminding you that each tick of the Ekman spiral is between 30 and 45 degrees to the right. Okay, when viewed from above, of course, remember to the right, and the direction will then appear clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. So here's a great way of viewing that, okay? So here's our original surface current. It moves in the direction to which the wind pushed it. It then spirals down the spiral staircase, 30 to 45 degrees at each turn, till it reaches the bottom of the surface layer. It will then be 90 degrees to the right from which it originated, therefore letting us know that that water, which originally was on the coast, is now pushing out into the open ocean. And that would, of course, match up where the gyre is not, right? The gyre is in the periphery. The gyre is all the way over here. So this is a good way of getting water into the middle of an ocean system. Okay, like putting stuff in the middle of the bathtub. If we look at this for the entire globe, okay, right now don't worry about the deep layer that you see here. Okay, we're going to get to that in a second. But when we look at this from an entire global perspective based on Ekman transport, this reminds us that the north equatorial current, that's our trade winds, okay, that's moving from our easterly to westerly direction, 90 degrees to the right, the Ekman pushes it into the center of the North Atlantic Ocean. Conversely, the south equatorial current, again, from the south trade winds, moves in the same direction from the east to the west, but these are counterclockwise. So when viewed from above, this right-hand turn pushes it again into the center of the South Pacific Ocean. For those of you interested in how this story ends and wondering where this water comes from to get to the equatorial region, it's eventually going to come up via upwelling from the deep water. Remember, the deep water is 80% of the total ocean water. There's another key component that we just have to add into the surface layer before we move on to the deep layer. The surface layer components are going to also include something that's sort of a misnomer, right? Something that meanders, something that is out of time and place, doesn't seem to want to be there. It is a pinched off, isolated cell of either warm or cold water, and we call it an eddy. Okay, the formation of an eddy is basically our explanation for saying, why are you having cold water in a warm water location or warm water in a cold water location? It literally means that you have a separate pinched off cell that doesn't match with the surrounding water around it, right? This is all warm water, and we had a cold water cell here. This is all cold water, and we had a warm water cell here. These are called eddies. Why do we even bother to talk about them? Why are they important? Well, hopefully you're realizing that if the surface layer of the ocean has 3 different temperatures, depending on where you are in the world, polar, tropical, or temperate, and the Ekman transport and the Ekman spiral is density dependent, meaning only the cold and salty stuff, or only the density, right, high density stuff falls down, we really need to make sure that we have different stuff, different temperatures, different salinities, different waters interacting. If the ocean was all uniformly one temperature or one salinity, the circulation in the ocean would stop. We would literally cease to move, and that would be extremely dangerous. We'd go immediately into an ice age. So eddies are really important because around areas, for example, this would be our Gulf Stream, okay? Around areas where you typically just have warm water, it's great to be able to add in cold spells or warm spells in the cold spells. It allows for circulation to continue. It allows for the density differential to allow the Ekman transport to still continue. There's another view of eddy in the same way. A little bit hard for you to realize what you're looking at first. Take a minute, right? So here's the east coast of the US. Here's Long Island, right? Chesapeake Bay. Here's Florida. So what we're seeing, this is the north equatorial current coming across. We have the Labrador current and some cold currents coming in from up here, not part of our original North Atlantic gyre. And you see that the north equatorial current connects into the Gulf Stream and allows this warm water to push up literally almost to us. But instead, cold water comes rushing down, and then in opposition, you get these distinct pinched off areas that don't necessarily match. What they're doing is they're showing us that there's a connection of eddies, number 2 and number 3, in mismatched spots. critically important, allows for circulation, and continues to allow our gyre to function. Another example of that same location. Two terms I want to introduce to you before I move down to the bottom layer circulation, okay, are the terms upwelling and downwelling. So remember, first we're talking about the surface layer of the ocean, okay? In the surface layer of the ocean, the very first movement of our water is wind influenced, right? Pushed by the wind. So they call it wind induced. Now, the gyres are moving horizontally, right? So the North Equatorial Current and the North Atlantic Current are horizontal wind-driven circulation. When you move down the Ekman spiral, you're now moving vertically, right? If you come up from the deep layer, you also are going vertically. So the vertical circulation is a different explanation. It can't be wind-driven in its depths. So it's induced by the wind because that starts the actual circle, right? That pushes the roulette wheel to spin. But then the density dependent allows it to fall down or rise up through the peak line into the deep layer, and it either comes up or down, again, depending upon the density. So these are pretty easy terms for you to remember. If something moves up, we call it upwelling. If something moves down, we call it downwelling. So if we go back and we think about that Ekman transport, okay, and we're moving based on an offshore push, okay, remember we originally start hugging the coast, then we end up 90 degrees from the original direction from which we started, so we're moving into the center, okay, from the original wind-driven source. If that happens, when it gets into the center of the ocean, it will go down the Ekman, and when it gets to the bottom of the surface layer, one of two things can happen, okay? It can either, again, we're looking at this water right here, okay? It can either be really cold and really salty, or one or the other, and it will be so dense that it will fall down to the deep layer, okay? That'll be another type of circulation we're going to talk about next. But what happens if it hits this spot at the bottom of the Ekman? It traveled down through the surface layer of the ocean, and it's not cold. It's not salty. It's not dense enough, right? It doesn't weigh enough to get down there. When that happens, it will literally go back up. Here it is. It upwells to where? The original source it started, right back to the coast. Okay? Same explanation is shown for you here. If, however, it gets to that section and it does fall through, it downwells into the next layers. Okay, so that's a good explanation to explain to you upwelling and downwelling. We have two main types of upwelling, coastal upwelling and equatorial upwelling. Coastal upwelling, that which is near the coast, typically on the western sides, as you can see here, right? So the west coast of Africa, the west coast of Europe, west coast of the United States, west coast of South America, okay? West coast of Australia. They're not in the exact same location, right? But the vast majority are going to be based upon currents that are coming from the deep to the coastal edge, bringing nutrients, a lot of food. This is responsible for a lot of fishing times, right? A lot of people know when these upwellings are occurring, and that is exactly when they'll fish. It increases primary productivity or food sources in the spring, which again allows for a lot of babies to be born, right? The seasons sort of predicate these things from happening, so the circulation is critically important. But what these are doing is as they're pushing up to the coast, they're really bringing nutrient-rich cold water from deep down to the actual coastal edge, okay? That's coastal upwelling. If we were going to have upwelling from a different section, then we would have to give it a different name, meaning if it wasn't coastal. So we know that coastal, of course, is colder and deeper coming to the surface, bringing increased nutrients and productivity, okay? It starts as wind induced, and of course it's vertical because it's coming from below to the surface. The opposite of coastal upwelling, okay, is going to end up being equatorial upwelling. Okay, so again, coastal upwelling is here. The opposite, the equatorial upwelling, is going to be westward flowing equatorial currents that get deflected to the pole. Then the deep water comes up at the equatorial region. Okay, so this is primary productivity and annual upwelling. Okay, reds are your highest. So look where you see it. There are some coastal regions, right? Here it is again, coastal, right? I'm not telling you that it doesn't occur at the coast, but it by and large makes this beautiful pattern right along the equatorial region. We call it equatorial upwelling. Again, all in the surface layer. This brings very, very extreme food sources into areas of the ocean that may have been pretty devoid of any food. Another view showing you the same path. Okay, remember, it's coming from the deep layer. Conversely, if we're not coming up, we must go down. So the water driven toward the coast will be forced downward, okay, or water driven in any direction that is highly dense is forced downward. It doesn't bring nutrients, instead it brings dissolved gases. This is still wind driven, still considered vertical because we're going down instead of up. In order to get to that layer, to then complete our circle, to join ourselves in our total ocean circulation pattern, we need to best understand what actually happens in the deep layer. So this is our deep circulation. Okay, so let's just do a quick recap to make sure we understand the ocean. Okay, I'll draw a picture down here. So if you remember back to the seawater lecture, okay, we had our surface layer situated essentially at the equatorial region and the subtropical areas around it. We had the peak necline, 18% of the ocean, okay, essentially keeping the surface layer separate from the deep layer, but extending us a little bit more into the temperate layers. And then the rest of the ocean, 80% of the ocean is considered deep. That's where we're talking about right now. What is the circulation in this layer? Okay, before we cover this entire section, let's recap what happens in the surface layer and in the peak necline. In the surface layer, let's make sure we understand what I just covered. Okay, that's all the material that we just covered. You're going to start with wind-driven horizontal circulation. I'm calling it a roulette wheel. It sits and moves horizontally in a gyre in the periphery of the ocean basin. It is made up of 4 currents. Those currents are all moving horizontally. 2 are wind-driven, 2 are density-dependent. After it goes around the entire gyre, material gets pushed toward the center, and material from upwelling and downwelling areas join it. When that happens, it circulates into the center and spirals downward because the density is pulling the heavier, more dense stuff, which means colder and saltier water, down. It goes down in the surface layer via the Ekman spiral. The bottom of the Ekman, again, we're still in the surface layer, we're still in number 1. At the bottom of the Ekman, it pushes it toward the center of the ocean, and then it allows it to have a vertical circulation. If it goes down, we call it downwelling. If it goes up, we call it upwelling. If it comes up at the coast, we call it coastal upwelling. If it comes up in an equatorial region, we call it equatorial upwelling. It's just telling us that we move from a horizontal to a vertical circulation, going around the periphery of the ocean basin and then allowing water to be pushed into the center of the ocean basin, all in the surface layer, okay? All in that top 2% of the ocean. If, however, after it goes through that entire process that I've explained to you, it is still cold and salty or dense, it can fall down via downwelling and go through the peak necline, and join into the deep layer, okay? Remember, this is our equatorial region right here highlighting. So it's telling us that this is happening at the equatorial region, that you have a downwelling, okay? So that's how water is getting into the deep layer in this particular section in the equatorial region. Now, how does it get there? It gets there literally based on, we're in our 3rd layer now, based on density. What is that density dependent upon? Look at this. This should be a term that you're really familiar with. Thermo, remember thermocline? Haline, remember halocline? So it's temperature and salt, or temperature and salinity circulation. In other words, the third layer is based on density. What is that density based on? It's based on salinity and temperature only. So if something's really cold and really salty, it gets down to the deep layer. Again, driven by density differences. These water masses do not mix easily, but they flow above or beneath each other, but they're still in the deep layer. Okay? Hopefully you're noticing that I have a number 1 and a number 3. Okay? In other words, surface layer of the ocean, the first layer, deep layer of the ocean, the third layer. I never said anything about the pycnocline. All I said was that water fell through it, or conversely, it could upwell through it as well. The pycnocline does not have circulation. The circulation in the ocean is either in the surface or in the deep. So that's why we're covering 2 areas with 2 types of circulation. I just want to make that very clear to you that the pycnocline, is like a gatekeeper. Stuff moves through it, right, up or down, but it doesn't stay there long. If you remember when I called it the peanut butter and jelly sandwich, the breads are the parts that have the circulation, the peanut butter and jelly do not. When we look specifically at thermohaline circulation, and this is a very important slide, okay, here again is the term. When we look at thermohaline circulation, we remember that this is a deep layer, and we're now introducing our 2 terms of upwelling and downwelling as they apply to temperature. So let's make sure you understand where we are in this figure. Okay, so this is 90 degrees north or south, okay, in our polar regions. Remember, at the surface of the poles, it's still considered the deep layer, right? Remember that when we talked about that in the seawater lecture? Because it's so cold and so dense, it cannot be part of the surface flow. So since it's cold and dense, it's going to have downwelling, vertical circulation, all the way down to the bottom of the ocean floor. Okay, in other words, under the North or South Pole. But what happens when it gets there? It doesn't just sit there. It goes to the bottom of the ocean floor and then circulates across the bottom of the ocean floor. When that's happening, don't forget, material is joining it and the water itself is heating up. Okay, now it's heating up at the surface, but you still have mobility because of it. And this is slightly warmer here than it is here. So it begins to rise. Now you have an upwelling. So here's your downwelling. Here's your equatorial. Here it is. Here's your equatorial upwelling. It goes through the thermocline, or if we were talking about salinity, through the halocline, or if you wanted to combine the thermocline and the halocline, we could easily say where it's going through the pycnocline. It then joins the surface flow and moves in the direction to which it is pushed across the surface layer until it cools again. As it cools, it becomes dense and it falls back down. So I call this the Ferris wheel. And a roulette wheel is sitting flat on a table and spinning. A Ferris wheel is still a circle, but it's up and down, right? It's vertical circulation. One side down, one side up. So there's your downwelling and your upwelling as it applies to thermohaline circulation. And that also helps you understand how deep water circulation, all of this, and don't forget all of this too, that's all deep layer, 80%, how all of that impacts your pycnocline, which is your middle layer right here, okay? And your surface flow, which of course does not cover the entire surface of the ocean. It's just the 2% that sits over your tropical and subtropical regions. We're looking specifically at the Atlantic Ocean, specifically the South Atlantic Ocean. And I just want to point out something called the Antarctic bottom water. The Antarctic is the coldest of all of our cold systems, right? In other words, the Antarctic is colder than the Arctic. And the bottom water there is also colder, okay, in general. Remember, that's a continent, so it also impacts our ocean systems there. As this flows along the bottom of the Antarctic or Southern Ocean, it connects with the South Atlantic Ocean all the way down. When that happens, this becomes the most prominent and heaviest, and therefore the fastest sinking of all of our downwellings. So this essentially becomes the most important of all of our bottom currents. We then have these layers, okay, again, called bottom water, deep water, right? We then have these layers that allow us to have these deep water masses that become critically important in our downwelling process. The single most important one is going to be the one at the bottom of the coldest ocean, or the Antarctic bottom water. When we look at this in the North Atlantic, we're not going to have the Antarctic bottom water, okay, because it's all the way down at the other side of the ocean, except, are we? Yes, remember the Atlantic Ocean is connected from the north to the south, and the south sits literally next to the Southern Ocean or the Antarctic Ocean. So this is showing you that the deep water circulation can get through entire ocean systems and literally all ocean systems, right? In other words, a cell of water can travel through all ocean systems on the planet before it gets back essentially to where it started. Okay, the system is completely interconnected. It's a little bit hard to fathom, right? So what we do instead is we show them in these ribbons, okay? We like to call them the conveyor belts. And it shows that our deep flow, our deep layer, and our shallow flow are actually connected. They're not literally connected. In other words, things don't just go up and down, top to bottom, shallow to deep and deep, right? Instead, to get from here to here, we might literally follow a zigzag path before we get back, like the craziest puzzle. And you now understand why. These currents are moving from surface to deep, from deep to shallow, and back again. You understand? Here's another view of the same thing. Here we are, if it helps you to always find home base. Here is the North Atlantic Gyre. Okay, here are 5 main gyres. Okay, they're sitting on the surface layer. Underneath, and again, they're reminding you that because they're warm and shallow, they're sitting on the surface layer. Underneath, though, here it is. This is our thermohaline circulation. And look what it does. It traverses the Southern Ocean in the Antarctic circumpolar gyre, essentially is what's traveling across it. But it eventually moves upward, which then allows water to travel to the surface layer via upwelling, joining the warm water, which circulates into other portions and other oceans. And look what happened. We just went from the Indian Ocean to the Atlantic Ocean. So in other words, deep water can circulate all the way across the bottom, especially in the Antarctic, because you can circumnavigate the planet there, never hitting land. It's the only place in the world that can. So this great ocean conveyor belt is essentially telling us that you can connect top and the bottom of the ocean in all portions. Another view of the same thing, reminding you again that you have a surface layer, that's represented here in red. You have a peak necline, and then you have your deep layer, which covers both poles and the Antarctic bottom water and all of the other deep waters and intermediate waters. They then can have inputs into the surface layer, and the surface layer, of course, can add to the deep layer, showing, of course, that the top and the bottom and the warms and the colds all can ultimately connect. What's interestingly pointed out, though, about this is how fast or slow you may or may not think it occurs, because the sinking of the water masses is offset by the slow rising for the warm temperature in the tropical zones. So the thermohaline circulation, while found in the deep layer, certainly impacts surface circulation. And surface circulation, although it doesn't occur in the deep layer, impacts the deep layer thermohaline circulation. In other words, the reds and the blues that you just saw in the figure before impact each other. Look at this time frame. Some people even use 3,000 years as the date. We believe that it takes approximately 1,500 to 3,000 years versus 1 year for a gyre in a surface layer circulation to circulate versus going through the entire deep layer of the ocean. We've never been around long enough to know if this actually works. These are all computer generated, and they're guesses based on how long we think that it will take for a cell of water, a total circulation of water, to get from, let's just say, the bottom of the Atlantic Ocean to the surface of an equatorial region. and back again. We believe that that entire path would take 1,500 to 3,000 years, as opposed to the 1-year time frame that it takes for a gyre to complete its path. So hopefully now you understand the ocean circulation. The next lecture will cover waves, which will then allow you to see how the movement of the water is occurring at the surface layer.